Today I'm going to give you the first of two lectures on organic chemistry, and hopefully after this lecture, if I'm lucky, at least you'll understand the joke that's on this slide. By the way, this is one of my favorite scripture verses in one of my favorite books, from probably one of the favorite chapter in that book. Likewise reckon ye also yourselves to be dead indeed unto sin, but alive unto God through Jesus Christ our Lord. What is organic chemistry? Organic chemistry is the chemistry of organic compounds. Organic compounds are those compounds that contain carbon and are part of most living things, which is why they have the name organic chemistry. They are generally formed frequently by non-living processes, such as geological processes or artificial processes, but they're central to the foundations of life. Biochemistry, which is the chemistry of life, is a subgroup or a subtopic under organic chemistry. Carbon is unique in its ability to bond with four bonds, and therefore the variety of compounds and the variety of reactions that can occur are quite significant. There are several different ways in which organic compounds can be expressed. These are three examples of what is known as a hydrocarbon. Hydrocarbons are organic compounds that contain only hydrogen, thus the hydro, and carbon, just the carbon. So, what we have here are three different hydrocarbons, which are shown in three different ways. There's a Lewis structure at the top, the ball and stick model in the middle, and the space filling model in the bottom. And these three are called methane, ethane, and pentane, and you'll understand where those names come from after this lecture. There are several different kinds of formulas that you can draw, and you will be expected to understand at least these three types of formulas if I were to ask for any of these three types. On the left is the expanded formula, in the center is the condensed formula, and on the right is the skeletal structure. Alkanes, which all three of these structures show an alkane, they actually show the same alkane, are hydrocarbons that contain only single covalent bonds. Since they contain only single covalent bonds between the carbons, they are saturated with hydrogen, thus they're called saturated hydrocarbons. The general formula for a hydrocarbon alkane is C to the N, NH to the 2N plus 2. Thus, for example, in this alkane hydrocarbon, we have 3, 6, 9 carbons, so it's C to the 9, H to the 18 plus 2, or 20. The same structure above can be represented in these three different ways, and I will expect you to understand these three types of structures. There are two types of hydrocarbon alkanes. One is the linear hydrocarbon alkane, and the other is the branch chain hydrocarbon. The one on the right, A, is a branch chain hydrocarbon. All the carbons are not in a straight chain. You cannot draw a straight line through all the carbons without lifting your pencil and going or backtracking. B represents a straight chain hydrocarbon. Hydrocarbons that are called straight chain hydrocarbons are those that have the carbons all in a straight line. These two have the same formula, C to the 7, H to the 16, but they have different structures. Therefore, they're called structural isomers. the two molecules that was shown on the previous slide are now shown on this slide with a skeletal structure. The skeletal structure is generally drawn in this way so that you can differentiate where the branches are. Every intersection point and every end point represents a carbon and the corresponding hydrogens. What would the skeletal structures of these two compounds look like? Take a look at these, and on a piece of paper, draw something that looks like this to represent these two. And I'll give you a minute to do that. Here are the skeletal structures for the compounds on the previous slide. On the left, you have a ring with one single offshoot, which corresponds to that single CH3 group coming off the ring. And on the right, you have a 5-carbon straight chain. Now take a moment to see if you can draw the condensed formula. Remember, the condensed formula is the one with the carbons and hydrogens shown, but it is not expanded. So what would the condensed formula of this compound look like? Here we have the condensed formula of the previous compound. Again, you see a ring with a branch chain coming off the smaller ring. Take a look at this skeletal structure and see if you can draw the condensed structure and give the chemical formula for this compound. All right, here we have on the top the condensed structure, and then on the bottom is the chemical formula: C to the 9, H to the 20. Now this is a table. There's a table like this in your book, and this is a table you will need to memorize at least the names. You don't have to memorize the boiling points, but you will have to understand or know the names of these, because as we do naming, you will have to have these names in your head so that you can start with the proper name of the underlying alkane. A single carbon is methane, 2 carbons ethane, 3 carbons propane, 4 carbons butane, 5 carbons pentane, and then it becomes a little bit easier because these names are familiar in terms of Latin or Greek words that you've heard in the past. So you have hexane for 6, heptane for 7, octane for 8, nonane for 9, and decane for 10. You will notice, just as a trend, that the boiling points increase as you get larger and larger compounds. And you will recall from our lectures many months ago on chemical bonding that the types of bonds, that intramolecular bonds that occur, are called London forces. The London forces increase as the size of the molecule increases. And that is because London forces are secondary to transient imbalances in electron distributions. And these transient imbalances lead to electrical attraction. And the electrical attractions become stronger as the imbalances become greater. And these transient imbalances increase as the molecule becomes bigger. And so you can see that the boiling point at each one of these gets higher and higher. as the size of the molecule gets bigger and bigger. Now, as I said before, when you have two compounds that have the same formula but have different structures, they are called structural isomers. The structural isomers are different in that there is a different arrangement of bonds between the carbons. You have the same number of hydrogens, the same number of carbons, but the arrangements of these are different. The longer the molecule is, the greater the number of different isomers that can be drawn. Now, it is possible to draw the same compound slightly differently and have not a structural isomer. So you can see here that there are three ways that you can draw the same compound, butane, but these are not isomers because the arrangement, that is, they're all linear arrangements of the same molecules, the same atoms. If you can draw with your pencil, for example, if you can take your pencil and draw a straight line through all the carbons without lifting your pencil or backtracking, like this, then these are all the same molecule. In our previous example of structural isomers, you will see that there is no way to draw a straight line through all four of these carbons without backtracking or lifting your pencil. So here you can draw a straight line, so this is butane, but here you can only draw a straight line through three, so it's propane with a side group, which we will talk about where the names of these side groups come from. And so the fact that you can draw three of these that look similar in this way does not mean that these are three structural isomers. These are actually all the same compound, all the same structure. Now, as we begin to talk about naming, you have to understand that there's a standard convention for naming of all organic compounds. And the standard convention for naming all organic compounds is called the IUPAC, or International Union of Pure and Applied Chemistry. This is a group that is formed whose job it is to develop standards for naming various organic compounds. And we will go through how these various names come about. But this technique of naming comes from this organization, and the rules for naming come from this organization. The first rule is that you find the longest continuous chain, longest continuous straight chain. So for example, it's 1, 2, 3 here, 1, 2, 3 here, 1, 2, 3 here. This does not count, because even if you went this way, it's still 3 or 3. Then there's 1, 2, 3, 4, 5, 6 there, and 6 there. And that is the base compound that where the name comes from. So if it's 3, it's propane, 3 again, propane, 3 again, propane, 6 hexane, 6 hexane. Then the substitutes or substituents that come off that are named separately. And so here is a chlorine. This is a methyl group. We'll talk about that in a minute. These are 2 fluorines, so it's difluoro, and bromine and chlorine. The numbering is done so that you can tell the person reading the name where the substituent or the side group is. So for example, you number 1, 2, 3 here, and you can number it this way. The numbering is generally done so that you have the smallest numbers. So for example, in this one, you start here so that you have 2, 4. If you started over here, you'd have 3, 5. So the convention is to start so you'd have the smallest numbers. So here you have 2, 4 difluorohexane. Here you have 1, 3, 1-bromo 3-chlorohexane instead of 4-chloro 6-bromohexane. The numbering is always done so that the numbers are the smallest that they can be. And as I said, these numbers indicate where the substituents are. So take a look at this and write on a piece of paper the name of this compound. Okay, first thing we do is we count the longest continuous chain of carbons. 1, 2, 3, 4. 4 is, if you look at the table, if you haven't memorized it yet, that's a butane. Then you note that you have a chlorine here and a bromine here. Now you can name from either end, but you want to select the end that would give you the smallest numbers, which would be to start numbering from this side. So it's 1, 2, 3, 4. So this is 1-chloro 2-bromo butane. So there's the 1, 2, 3, 4. 1-chloro 2-bromo butane. So what is the IUPAC name for the following compound? You'll do much better on these if you try it yourself first and then see what it is when I go through it. Okay, let's count. We have 1, 2, 3, 4, 5. So that's pentane. You have 2 bromines here and an iodine here. Again, you want the smallest number, so you're going to start from this end. 1, 2, 3, 4, 5. So it's going to be 2 iodo, 3, 3. You have to put 2 3s to tell them that both bromines are on the same carbon. 3, 3 dibromo pentane. So 2 iodo, 2 iodo, 3, 3 dibromo pentane. Notice that if you didn't have 3, 3, you could put bromines on other carbons as well. So it's important that you have both 3s in there. Now, as I said, you have these side chains that come off, and the side chains are named in the same way that the underlying alkane is named. So for example, the 1-carbon alkane is methane, so the 1-carbon side chain is methyl. 2-carbon 2-carbon alkane is ethyl or ethane. 2-carbon side chain is ethyl. 3 would be propane, propyl, butane, butyl, and so forth. It's one less hydrogen is what that should say. I'm sorry, that's a typo. I typed the wrong word there. These do not exist by themselves. So here's an example of a name or structure that has a side chain. Again, remember you count the longest contiguous carbon. If you count 1, 2, 3, 4, 5, 6, that's 6. Well, you'll say, well, why not 1, 2, 3, 4, but it's only 5. So the long 1, 2, 3, 4, 5, 6 is that way. But notice if you count it this way or this way, it actually ends up being the same name. So you have 6, so that's hexane. This is a 2-carbon side chain, so that's ethyl. It's on the 3-carbon. If you counted from the other end, that number would be 4, and that's not the smallest number, so you count from this end. So you have 3-ethyl hexane. So why don't you see if you can give a name, an IUPAC name for this compound. All right, let's take a look at how we would do this. The longest contiguous chain. So let's start up here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's a possibility. 1, 2, 3, 4, 5, 6, 7. That's not as long. 1, 2, 3, 4, 5, 6, 7, 8. So it could be this way, or it could be straight across. But you'll notice again, like the last example, whether you count it like this or count it straight across, you end up with the same answer. So 8 is octane. If you count from this end, this is the 4th carbon. If you count from this end, it's the 5th. So you want to count from this end. 1, 2, 3, 4. 4, this is a 3-carbon side chain, so that's propyl. 4-propyl octane. 4-propyl octane. This table is in your book. You will have to memorize this. So there's 2 things that you'll have to commit to memory. The first is that table that shows the underlying alkane names, methane, ethane, up to 10. So there's 10 of those. They are very easy to remember because they follow a particular pattern. And once you know those, these are also fairly easy to remember, up to the 4-member side chain. Now, where it does get a little bit dicey is where you have these 2 variants of the same 3-member chain. So methyl and ethyl are pretty easy. N just means normal, and it means that the first or last carbon is where the bond comes off, or where the hydrogen is missing. Iso means it's the middle carbon where the hydrogen is missing. So here you have N-propyl. This is isopropyl. And I'm sure you've heard of isopropyl alcohol, and I'll show you what that means next week. Now with butyl, you actually have 4 different possibilities. You can have N-butyl, which is just like N-propyl, a bond on, or the carbon or the hydrogen on the end is missing. You can have sec-butyl, which is either this carbon or this one. They're both the same. One is just a mirror image of the other. You can also have a butyl where one of the carbons comes off the side and then it's on the end like this. So this is isobutyl, just like this is isopropyl with the middle there. And then lastly, you have what's called tert-butyl. You have 1, 2, 3, and then the carbon in the middle, and this comes off. So this looks like a little Christmas tree off the side of a main chain. So there are 8 here that you'll have to know. So that's a total of 18 things you'll have to memorize for this week. The number system is again used to show where on the main chain the alkyl group is attached, just like the number system was used to show where on the main chain a bromo or a chloro or another substitution was attached. So for example, here we have a 7-member chain. So this is heptane, and this is 1, 2, 3. If you counted from the other end, this would be 5. Again, you go with the direction that has the smallest number. So this is 3-ethyl heptane. If you have several side groups like this, the main chain is in the middle here, and so you have 5 in the middle, so that's pentane. And you have, again, you can count from either end, and if you count from either end, you actually get the same answer. So here you have 2, 2, 4 trimethyl. There's 3 methyls, 1, 2, 3, 2, 2, 4 trimethyl pentane. And then lastly, you have this one, 1, 2, 3, 4, 5, 6, 7. So it's heptane, the 4th carbon, regardless of which way you count. And instead of being from the end, it's in the middle. So this is isopropyl. So this is 4-isopropyl heptane. And as I said, the alkyl group never stands on its own. It's always attached to a main chain. Now this is how we refine or isolate the various compounds that I showed you before. You recall that the longer the carbon chain, the higher the boiling point. And as it turns out, the side chains frequently have that kind of effect as well. So the crude oil that comes out of the ground comes in the bottom here, and it's heated to a very high temperature, 425 degrees. As it rises, it's cooled. And as it's cooled, the large hot chains come off here, give you fuel oil. The next larger is diesel. The next larger is kerosene. The next, naphtha. And the last is gasoline. Gasoline, in this situation, being the smallest molecule of the group in here. And then the gas comes off the top. And you'll see up here is the smaller molecules with lower boiling points, more volatile. The larger molecules, higher boiling points being down here. And this is what's called fractional distillation. So at each tray, a different fraction of the organic compound is taken off. Now, chemical alkanes can undergo several different types of chemical reactions. One common chemical reaction that you're expected to know and understand is called the substitution reaction. Here you have ethane plus chlorine gas plus some source of energy leads to the substitution of one of the hydrogens by chlorine in the formation of hydrochloric acid. This is known as a substitution reaction because the hydrogen is substituted by another element, in this case chlorine. Now, let's talk about everything I've said up to this point had to do with alkanes, A-N-E. Now we're talking about alkenes, E-N-E. And if you're astute and looking carefully at this model, you see that immediately that the difference is these double bonds, here, here, and here. An alkene is an unsaturated hydrocarbon molecule that contains at least one double bond. It's unsaturated because it doesn't have the absolute largest number of hydrogens that it could possibly have. It's not saturated with hydrogen, and so it's called unsaturated. You have, again, this is the expanded view, the ball and stick view, and the space occupier, space filling view. You notice that here's 2, 3, and 4. Instead of ethane, it's ethene. Instead of propane, it's propene. Instead of butane, it's butene with a 1. Okay? Now the 1 is there to show you where that the double bond is here and not here. Now if the double bond was over here, it would still be 1. But if it's here, it's 2-butene. Now the hybridization that occurs, now previously all the alkanes, the hybridization that occurs is sp3. So for single bonds, that is for any single bonded situation, the hybridization of the carbon in that situation is sp3. The hybridization for any double bond is sp2. And the geometry follows those rules that we learned in previous chapters. Now you can take ethene, which is also sometimes called ethylene, and take many of these and with a catalyst link them together and form a compound known as polyethylene. Now, as I demonstrated a couple of slides ago, the name for the alkene is derived from the corresponding alkane, and you just substitute the suffix ene for ane. So ethane is now ethene, and some kinds called ethylene. This is a more slang term. This is the correct term. If you use either of these, you'll get it right on a quiz or test. Propane now becomes propene. If the double bond is over here instead of over here, it's still propane. It's not different. It's the same as if you just flip this molecule over. But once you get to four atoms, 4 carbons, you have to tell people where the double bond is. And so this is 1 butene. This is 2 butene. Now over here, this is not 3 butene because this, if this is over here, is a mirror image, and so it would also be called 1 butene. Now once you develop compounds with double bonds, you have a new phenomena that can occur. This phenomenon is something called a geometric isomer. This is not a structural, isomer, but it's geometric. Notice that the 2 methyl groups are on the same side of the double bond in this compound and on opposite sides of the double bond in this compound. Now the name here, it's still a single straight chain. It's still 2-butene and 2-butene, okay? However, chemically, these 2 compounds are different, and therefore they have to be distinguished from each other. This difference is called a geometric difference, and it's illuminated by this naming. If they're on the same side, it's called cis. If they're on opposite sides, it's called trans. So a geometric isomer is when 2 or more compounds differ from each other in their arrangement of groups with respect to a double bond, a ring, or other rigid structure that cannot change its shape. So this is the rigid structure, and this is the different. If this were a ring in the middle, it would be the same situation. The models show the structural and geometric isomers for butene. So these are the 2 structural isomers, 1 versus 2, and then this is the geometric isomers for 2-butene. Substitution reactions can also occur in alkenes. This is a substitution reaction for ethene plus chlorine gas. The 2 chlorines both replace the double bond, and you have 1,2-dichloroethane. This can also occur in a situation like this. Take a moment and write down what you think the product of this substitution reaction would be. Okay. It's going to be one of the chlorines is going to be on there here. One of the chlorines is going to be here. This name is actually not correct. I'm sorry. It's going to be 2. It's going to be 2,3-dichloropentane. This is incorrect right here. The correct answer here, you'll have a chlorine here and a chlorine here, so it's going to be 2,3-dichloropentane. Sorry about that. Oh, I'm sorry. I didn't read the question. That's my bad. It says the name of the reactant and the product. This is the name of the reactant, and that is correct. You have one and the other on this side. They're on the same side, so this is 2-pentene, and since these two are on the same side, it's cis-2-pentene. If this was over here on this side, it would be trans-2-pentene. And then, as I said, the 2,3-dichloropentane will be the name of the product, which is shown right here. Sorry for the confusion on that one. I didn't read that question very carefully. Okay, let me read it carefully this time. It says, what is the IUPAC name of the reactant, that's this, and the product of this reaction? Now, the way this is drawn in the expanded notation, there's no way of knowing whether these are opposite each other in the cis configuration or the trans configuration. So this is 1, 2, 3, 4, 5, 6, so that's hexane. You got a double bond, so it's hexene, and it's 1, 2, 3 hexene. If this was up here and one was down here, it would be trans 3 hexene. If it's on the same side, it'd be cis 3 hexene. I've written it as trans 3 hexene, however, without showing it in a geometric arrangement, you really can't say that for sure. Now, once you do the substitution reaction, you're going to put a chlorine here and a chlorine here, so you're going to end up with hexane, so it's going to be 3,4-dichlorohexane. All right. The third straight chain or alkane-like molecule is called an alkyne. Alkynes, if you're astute, shows a triple bond. Triple bonds have a sp hybridization and are linear. So you have a triple bond, you have an sp hybridization. These again are named like the others, so that this would be ethane if it's a single bond, ethene if it's a double bond, and ethyne if it's triple bond. It also has the more common name of acetylene. So an alkyne is a hydrocarbon molecule with one or more triple bonds. Now again, you can have cis and trans when you have triple bonds as well. This is the simplest alkyne. It's called ethyne or acetylene. As I said, the name for the alkyne is the same as the alkane based on the number of carbons, but you substitute the yne for ane suffix, and you determine where on the molecule the triple bond is by using the numbering system. So what is the name of this? You have 1, 2, 3, 4 carbons. So that would be butane if it's the single bond, but it's butyne, YNE, and to show that its triple bond is not here or here, but is here in the middle, it would be 2-butyne. What is the hybridization for the carbons in this molecule? This carbon has a single bond and this carbon has a single bond, so the hybridization here and here would be sp3. The hybridization here would be sp. So carbons 1 and 4 are sp3 hybrids, while carbons 2 and 3 are sp hybrids. So, hybridization determines bond angle. Now you have 5 carbons here. You have a triple bond here, a single bond here, a double bond here, and a single bond here. So here Carbons 1 and 2 would have sp hybridization. Carbons 3 and 4 would have sp2 hybridization, and this carbon would have an sp3 hybridization. Carbons 1 and 2 are sp. Sp is 180 degrees or a straight line. Carbons 3 and 4 are sp2. Sp2 is 120 degrees or bent. And then sp3 forms a tetrahedron. And so the angle of one of those angles of the tetrahedron is 109.5 degrees. Alkynes can also undergo substitution. If enough product is or enough reactant is available, you can completely substitute all the bonds, extra bonds, with the substituted material and form a compound that is saturated with bromine. We'll finish up by talking about ringed compounds with double or triple bond, ring compounds. Ring compounds that have hybridization are called aromatic hydrocarbons. This is an example of the hybridization that occurs. So you have here your double bonds here, here, and here, and then it's here, here, and here. And so this is an aromatic compound or an aromatic hydrocarbon. It's a compound that has a ring structure and exhibits bonding that must have resonance or hybrid concepts of resonance with delocalization. So these are the two resonance structures for this compound. This compound is actually called benzene. The 3 valence electrons, all these are sp2 hybrids, and then the extra electrons that occur actually make a lap around this track in this manner. And so what you have here are 3 valence electrons with the sp2 hybrid orbitals for each carbon. So each of these angles are 120 degrees, and they form this sigma bond network. The 4th valence electron of each carbon is shared with the adjacent carbon in their unhybridized p orbital, forming a pi bond. The pi bond is equally shared here and here, or here and here, etc. Now to show this, they draw it this way. So this is the condensed structure for benzene, and what this circle denotes is the resonance that occurs. Instead of drawing the 2 different structures every time, you just draw this circle, and that says that there's a delocalized electron that's present. These are some common derivatives of benzene. This is toluene. It can also be called methylbenzene. This is xylene, or 1,2-dimethylbenzene, and this is styrene. And this little side group, I don't actually know what the side group is called, but the importance of styrene is the fact that it's used to make polystyrene, which is a synthetic that's used in a lot of various industrial uses. Toluene and xylene are important solvents. If you substitute nitrate groups on 3 of these carbons, you have something called trinitrotoluene, or TNT, which is an explosive. This is one of the 3 isomers with the substitution of toluene with chlorine. Okay, so you have toluene here, and then you have a chlorine substituted here, and it's shown in the condensed structure this way. So without the chlorine, this is toluene, you add this. Now this is called 3-chlorobenzene. You start with where the methyl group is, it'd be 1-methyl-3-chlorobenzene. And so you have 1, 2, 3, and it's chloro. Or you could call it 3-chlorotoluene would be the better way to do that. I had a mistake here. This should be called 3-chlorotoluene or 1-methyl-3-chlorobenzene. Another way that these are named is to say this is the ortho, meta, and para position. So this methyl group is the one place, or the starting point of the ring. The neighbor to that is called ortho, the next is meta, and the opposite is called para. And so this would be ortho, meta, so meta-chlorotoluene, or 1-methyl-meta-chlorobenzene. The other two that can form are shown here. This is 1-methyl-2-chlorotoluene, or it can be called ortho-chlorotoluene. This is 1-methyl-3,4-chlorobenzene, 1-methyl-4-chlorobenzene, or para-chlorotoluene. Here we have benzene, and you've added or substituted bromine for that. You have the three different names here. This would be called 1,2-dibromobenzene or ortho-dibromobenzene. This is 1,3-dibromobenzene or meta-dibromobenzene, and this is 1,4-dibromobenzene or para-dibromobenzene. So on the left you have 1,2-dibromobenzene or ortho-dibromobenzene. The middle is 1,3-dibromobenzene or meta-dibromobenzene. And the last one, or one on the right, is 1,4-dibromobenzene or para-dibromobenzene. This is the last slide that I will show you today. Next week, we will talk about the other substituted compounds. These will include such compounds as aldehydes, alcohols, esters, organic acids, and we'll go through how those are drawn and how those are named as well. I want to thank you for your attention, and if there are any questions, please make sure you bring them to class.